Am I live? Just finishing my lunch. I'm going to start trying to stream around 2 o'clock every day, so whether I'm eating lunch or not, we're just going to get started. Welcome back. Welcome back to Practical Bayesian Modeling. I'm here just live streaming my way through, wrong book. Live streaming my way through Bayesian Cognitive Modeling, a practical course by Michael Lee, Eric Wagenmaker, working on saying his name, either or, where I just practice going through each of the exercises in the textbook in order to start familiarizing myself with how do we construct, using probabilistic programming, how do we construct cognitive models that can inform our research questions. Thus far, I've gone through part 2, parameter estimations, where we looked at binomial rates and Gaussian processes. Now we're looking at some examples of potential data analysis that one could run. And we're in part 5.3, and today, depending on the exercises, we might just make it through chapter 5, so we can go to latent mixtures. So let's check out chapter 5 then. Here we are. So we're going to be looking at a way to capture inner rate of reliability, that being the Kappa coefficient. Here just specifies some of the history of the statistical test and how we go about capturing it. We have P sub O, which is the observed agreement, which is equal to all of the observations. So observations where both agree, observations where they don't agree, observations where they don't agree but in the other direction, and observations where they agree but in the other direction. So here is when they agree, so when they both say, for example, yes, and they both say no, and then the total amount of times they say something is what we have here. And then we have what we expected here. And then Kappa is just what we observed minus what we expected over 1 minus what we expected. So bounded, another important thing to consider, especially for modeling here, is we might specify Kappa as being -1 to 1 with values below 0.4, and then it just gives us some sort of conventional statistics or conventional interpretation levels for varying levels of Kappa. And let's go and take a look at the graphical model here then. So here's the Bayesian graphical model for Kappa. This is probably the first model we've seen that was this dense. I mean, dense is not the right word, just fill. It's very full. And so we have the 3 key latent variables here. Okay, so alpha, beta, and gamma. Here's the rate. Rate of 1. So this is a rate agreement. And agreement, but agreement for 0 and agreement for 1. And this is, I guess, the base. They call it surrogate or gold standard, so whatever your baseline measure person is, whether they chose 1 or 0. And from these values, the double circle means that the parameter is deterministic, meaning that it can be estimated from all the information that we gather from the latent variables. So these 2 are estimated from a combination of these 3, and from these 2 we can calculate k. How we do that with that information is here. Each of these values are a beta distribution from 1 to 1, beta distribution 1, 1, which is uninformative, prior, eating my salad, put my microwave, eating my salad. So from each of those coefficients then, we're able to calculate the probabilities, which are represented by this pi, probability A, B, C, D, which we spoke about up here. All of which we're able to estimate from y. The y multinomial distribution, these 4, and then the number of observations. All right. Yeah, and this is the expected, and this is the observed, and this is Kappa. So let me pull up the code then. books. Student guide. All data. Oh, we're not in student guide. We're in Bayesian Cognitive Modeling, perimeter estimation, data analysis, and we're looking at Kappa. It's going to be Kappa. Here is our Kappa model. Here is our Kappa jag. Good. Let me set up the panel. Also, I'm going to pull up the Stan code. I spoke about that a little bit yesterday, but Stan is another language other than JAG that we can use in order to do our model specifications. And I'm interested in trying to learn these along with one another. So I just want to explore that code as I run it here. Stan code here. Inject's going here. So let's start by just looking at the model. So we want to specify alpha, beta, and gamma, each of which are beta distributions. Then the probabilities for each count. So P1, which is A, B, C, and D, is equal to alpha times beta, etc. And now we have the count data itself. So for each one of our 4 probabilities, we're going to make a multinomial distribution of pi corresponding to one of the 4 and n number of observations. And then we're going to specify some of the determined measures, which x of I, xi, to the observed, and this is the expected, and then lastly we have kappa. It's pretty straightforward. I'm going to set my working directory. I'm just going to run this. Cannot open. Oh, I seem to have set my working directory in the wrong location. Great. Let's just head back over here. Reset my working directory. There we go. Oh. What's this? I'm not interested in that. I would much rather just get a printout. There we go. So we're going to get alpha, beta, gamma, and what we care about here, kappa. Kappa here, 0.6. We look at interpretations. 0.4, 0.75 is fair to good. So we're in the range of being high, fair, and then moving. We're definitely always in the 95% credible interval. Kappa maintains being fair and then moves into being pretty good. So we're on the higher end of agreement here. So this is the influenza. This is for the influenza data set. Yeah? Oh, let's read about what we're actually doing this on. Influenza clinical trial. So we're evaluating rapid bedside tests for influenza from a sample of 233 children. Of 18 children who had influenza, the surrogate method identified 14 and missed 4. Of 215 children known to not have influenza, the surrogate method correctly rejected 210, but falsely identified 5. Given these rates, we have a probability A, B, C, and D corresponding to these 4 values, and we want to examine the posterior distribution of the interesting variables to reach a scientific conclusion. Pretend you're a consultant. So my take-home message would be that we have moderate to fair to, what is it? We have fair to good, leading on excellent agreement across the abilities of the 2 methods to evaluate influenza. So both of which do it fairly, both methods for capturing influenza are not that variable or not variable and high. So high here being good. So good with the probability of it being excellent high. It's fairly precise. And I would recommend the rapid bedside test as a way to identify influenza. Now we can take a look at the hearing loss grant or assessment trial. So these 4 values here are A, B, C, and D. That'd be nice. Oh, and just so we're clear, something that I didn't notice on here. Kappa is Cohen's. If we calculated this and did a point estimate, we get 0.73. So our posterior distribution covers that and is a little lower. I'm going to find some code.
I know. That's like a really. But like they did help sell me in this school. I think that's kind of funny.
I was looking for some old code. Where I plotted out these things using ggplot. I just don't see it.
I think it's like it's something very inspirational.
Is that what it is? No, it is.
I'm pretty sure it's like Drexel where you achieve or some bullshit.
Oh, Drexel, I was thinking Rutgers. Rutgers is like, they're nice. Drexel is like something.
Oh, it's definitely just like Go Dragons if you're talking about like that. But all of the like little
They'd be big enough for the company and do one every couple of years. If the shit happens when you turn stuff around, it's
Mm. Looks like my lab can pick up my roommates. Nice. Maybe I can fix that.
I can see causing some issues if you're like a bigger person and you go to school with a math test and shit that yeah. I don't really see that often. Where it's I don't know. I think it's fine too. There's one college that like rebranded their mascot
There we go.
and they rebranded their colors like pink and something and then put kangaroo.
oh my god.
And like all the alumni were super pissed. But, they're like, what kind of bullshit is this?
Oh my god.
Pink kangaroo. We need a fucking dragon.
Very nice goal.
I think I really got to work on my levels too, and some stream side stuff. I think sometimes I'm just picking up too much other stuff in the background, and I'm not sure how to get that. Or maybe in post or something. Not that I know how to use that term
My
yet.
high school rival, the West Shore Bulldog. Same logo.
There's a school here in Philly. They just love them.
I do notice though, I do pick up my roommates talking. Or barking.
Is that what you guys do with the plugin?
Literally, yes. We have this thing called Call the Dog. Go dog! Sick 'em! And like a whole stadium erupts. Yeah.
Except his church has
Hmm.
yeah.
And then Kappa is going to be from -1 to 1.
Yeah.
I remember my manager at Maryland went to ship, so one time he was like visiting after his college and was placed in SEC school. And he was like, they were getting ready to do the pool, and he was like, do you really do your
Maybe I can just.
suit? He's like, yeah, he's like,
Does that help? No, that doesn't help. LOL.
I wanted a burrito too.
Nice.
Why are you LOLing me?
I could hear the dogs on my stream.
That's funny.
I just heard woo.
Go dog.
Go dogs. That's interesting. I see. It's because I need this simulation list. Doop. Here we go. And then I could even add geom. What is it? Here, would be the point estimate that we'd get using Cohen's method. And then here's the posterior distribution for Kappa. So you can see that they align quite nicely. But now I get this distribution of certainty I have surrounding my estimate. So I can be, not only do I know that the estimate is good, in the sense of the interpretations that were listed in the text, but I know that, or I can be confident that it doesn't go below a fair, or it's not likely to go below fair for my parameter estimate for Kappa, which is cool. Oh, okay. Let's look at the hearing. So that was for, let me change the data back so I can just see it. Let's see here, not 0. All right, so now hearing loss, and we're going to look at how nurses assess relative to expert assessments. So we want to check the quality of nurse assessments. The gold standard here being experts, the nurse being the surrogate. And then it gives us the values for A, B, C, and D, and give me a take-home message. So let me look. Looks like, ooh, low agreement. To a pretty poor agreement. We would say then that nurses are not or don't agree with expert assessments. So it would be my recommendation, given this, and we can be fairly confident about this too. It's like very tight distributional wise. It would be my recommendation then that we train nurses better. It's very poor agreement. Yeah, just beyond chance, really. And in fact, Yeah. Just beyond chance, it looks like. Last data set is rare disease. Suppose you're testing a cheap instrument. So I'm going to be assessing the quality of this instrument in order to assess rare medical conditions. Well, one thing special about this approach is that we have no measurement occasions for A and B. Oh, well, we do. But none of them were able to capture that someone had the condition. Something neat then, I figured, was that in the description of the interpretation for the Kappa coefficient above, we spoke about interpretation from below 4, interpreted as poor, beyond chance. Well, here, we actually have some evidence that it might be 0. So the Kappa coefficient for the point estimate was 0, yet this gives us a sense of the degree of uncertainty we have surrounding each of the of this coefficient estimate. So we can see it might be 0, it might be negative, and then there's even a chance that it's a little larger. Right, so the book says, the data is noteworthy because the disease has never been observed, right? So there are 2 0 cells. This poses quite a challenge for frequentist estimators. In order to deal with this problem, 0 counts, a frequentist might add 1 to each cell in their design, but this is basically fabrication of data. So here we have an attractive property of using a Bayesian approach because we're able to still get an estimate of Kappa, a posterior distribution for Kappa, even when we didn't observe any values here. So let's go take a look at the stand code then. Cool. So here's the model. Discrete variable, lower bound, 4, lower bound 0, and we have 4 observations. We have the parameters for alpha, beta, gamma. And then we have transform parameters here, where simplex, as indicated up here, is a data type. It's similar to a vector, but all of its elements equal 1. So we have real values. And then we have probabilities. So these are considered transformed parameters. So v1, same thing, just we have arrows here because we identify that this is deterministic, right? Instead of equal signs. And derived measures, expected, observed, and kappa. In addition to the parameters, then we have our model specification here. Data model parameters. And each of these are priors, beta, uniform distributions. And the data comes in the form of multinomial by phi, or pi, which is each of the 4. Cool. All right. Next example, we're going to look at a very simple change detection model where our main interest is just identifying a particular time point where the time series differs significantly such that it violates some sort of threshold that we specify a priori. And so we'll make a number of assumptions here in doing this. It looks like the graphical model here is demonstrating that we have means from 2 samples, which are uniform Gaussian distributions, and we have a shared estimate of precision, and then we have this uniform distribution to represent the which is the time point where change happens. So we want to know where tau is, right? And then we have counts at each time point. So each point in time, we have some count of information. And that count changes over time, and we want to know the point tau at which the count changes such that it meets some threshold, and now it can be considered part of the mean 2. So what's mean 1, what's mean 2? We're assuming the equal variance across these two things, but it's basically what the model's saying. Yeah. Okay. So let's pull up the change detection. Let's see what it looks like. Oh no. I really gotta figure out this pane layout thing. What's the jag? I like the jag over here. Oh, tell me I just did it again. I'm over it. Let's see. Oh, no way. There's a keyboard shortcut. Oh, nice. Check this out. Command F7. Oh. Nice. Okay. Never mind. We're back. Command F7, people. change your life. Can I do that multiple times? On just one. Like, yeah, one. Worth it. Alright. So we're gonna get the bug output. It's gonna give us the mean average tau. It will give us the average for each of the first half and the second half, and then it's gonna plot it. What does that look like? Oh. Nice. Essentially, I might as well print. Average of mean 1, average of mean 2. You can see that here, lower average. And then here is the change threshold, where at around 700 something is when the counts sufficiently were low enough where they were identified as being different. Lower than 712. At 712, that's when we started estimating a different time point. Take a look at the graphical model. So we use a for loop here. So our time points are coming from, here's the counts. So counts 1i and 1n. The counts are distributed normally with an average equal to mu and then this is going to be equal to either mu1 or mu2, and then the same value for the precision. And now for each of those, we're going to use a fairly uniform distribution for priors. And then we have precision here, inverse gamma. And then we calculate sigma from the precision. And now here, for an observation, so let's say 1, use the step function. So z is going to be equal to tau, the value at a given time point the count at a given time point minus tau. I think. What's the data look like? So here's the data done. We have 1,178 observations. Here's the count over all the observations. We'll use this called scan. So we scan this text file, which gives us the vector. We check the length of the vector, and then t is just going to be equal to 1. So time is equal to 1 to the length of the vector. So it's just a vector size 1,178. So let's talk through what this is doing. Because we identify z using step. I don't know what step is. I don't remember. Step. Function returns 1 if its agreement is greater than or equal to 0, and 0 otherwise. So z1 variable serves as an indicator for mu. Therefore, it needs to take on values 1 and 2. This is the reason z is transformed to z1. So z helps us identify if a time point if there's a significant difference between the time points. So it's greater than or equal to 0, turns to 1. So if the difference between the time point we're at and the threshold, so if I subtract the threshold from time and I get a value that's equal to 0, meaning that there's no difference between the threshold and the time point I'm at, or I get a value where even when I subtract tau, I still have a non-negative value, then z is going to be equal to 1. So we end up with a vector z that is just a bunch of zeros and ones. And then we feed that in. So because mu is parameterized as being represented as mu, either 1 or 2, we reparameterize z into z1 so that z's at 0 are equal to 1 and z's at 1 are equal to 2, thus mapping back on to the group means that we identified above. And then lastly, we just have to set a prior for tau, and we choose a uniform distribution. So we allow it to be any value between time point 1, or time point 0, and time point 100 or 1,000 something. And you can imagine how this could change if we had some information or intuition about precisely what was the range to when we'd expect to see some change over time. So let's draw the posterior distribution for the change point and standard deviation. So it wants me to just draw those. I have some code over here that'll let me do that. Just opening up ggplot and patchwork. And then I need the sims output, right? And I need the output for tau. I need the output for mu1. And I need the output for mu2. And then I'm just gonna make graphs. Now we'd expect no expectation for the distribution of tau, but I'd like if these were scaled similarly. So taking a look here, I'm just going to pick 25 to 40, just so they look alike. And in fact, I'm going to write this like this. There we go. Now we'll get the plots for the difference distribution. Why not? All right, we got P1. What's breaking? P2. There we go. B2 is breaking because just not accessing it right. Mm-hmm. Sure. Booyah. Now we have the average for 1, which is higher than the average for 2. And then we have the distribution for change, which tends to be around this time point, but also could be higher. Another candidate up here. Looks like. Upper sevens. It also wants the standard deviation. Great. That would just mean a P4 plot. Where P4, no limits. And I'm going to be looking at sigma. So this is going to be the variability in the means across the common means. And then I just need to extract sigma. Make sure that extracts. And make sure that plots. Make sure that 6. Cool. Figure 5.7 shows the mean of the posterior distribution for the change point. This is the point in time where the two horizontal lines meet. Can you think of a situation in which plotting a procedure can be misleading? I'm not really sure. So pre-imposed change, I mean, it's arbitrary, right? When we estimate this score from the data, so one thing that the book talks about then as being a potential or situation here is if there's a lot of variability around the measurement. So when there is So if we suggest that tau is a hard cutoff, it doesn't leave room for there being uncertainty surrounding what is the potential or viable taus. And this is especially important when there's a lot of uncertainty around the location of where this time point could be, where this change point could be. And even if we look at tau here, this kind of also helps us build an intuition for why this might be the case, because we notice that there are two humps for viable possible options for, or probable options for a change score. So the most probable options for change scores are here and here, but not here, right? But why is this the way it is? Couldn't it just be a bigger distribution? Imagine that you'd apply this to a data set that has two change points. What would happen? You would have three averages. It could be the case where you move down and be all the way up and then down, or right, so something has to be wrong then. No. So it's not the case we're asking, could we identify two specifically or intentionally identify two change points. It's that, what if we just specified it the way we did and then we identified two change points from that? Something has to be wrong. Because the way we specified our model clearly only allows there to be one or the other, right? We saw in that step function where we indicated threshold either is one or the other. So if we saw two, then something about how we group the data is incorrect. It could also be the case that there are three, right? But we're not specifying three, so we could go and check that too by making a model that intentionally specified three. And one of the mechanisms we have available to us to be able to check that is using information from posterior predictive checks. So once we specified a posterior distribution, we can go and test with some sample data, like resampling procedures, and see if we can identify this third group, and then backtrack. Let's enter data. How many questions on that? All right, well that's good, I think. So we did Kappa coefficient and change detection today. And then tomorrow we'll do sensor data and recapturing planes. That way we have this nice 2 and 2, and then we'll start chapter 6 the next day. Perfect. So, all right, today we went over using the Kappa coefficient, and then we went over developing a little change detection algorithm or inference tool. And we saw a couple data sets where we could use this for Kappa coefficient, and then we saw the potential pitfalls of specifying a single change point when in reality there might be two, and what sort of things would we want to consider moving forward. And we wouldn't have been able to identify this if we didn't plot this tau, right? Unless this isn't what it's talking about in the exercise example, it's just generalizing beyond this. I'm just talking more about a hypothetical where there was really just two taus, like we saw one over here at 600 or something. These are fairly close to one another, I think. Either or, that would be procedurally the sorts of things that we'd want to do. Great, so that's it then for today. Thanks for coming, and now we got that sweet keyboard shortcut, which is, just to remind myself, Command F7. Yeah, so Command F7 to add this little, to add another source panel to the side. Super useful. I'm gonna be trying to use that more often now. Thanks for stopping in. I hope you enjoyed. Let me know if there's anything that you'd like me to cover moving forward, or try to focus on to be more clear about what I'm talking about. I myself am learning these things as we go along, so any feedback that you have is helpful. Thanks again, and I'll see you tomorrow. Bye.